This is lecture 36. Okay, so in the last class we have actually seen this high swing voltage mode output driver. Okay, so there were a couple of questions at the end of the class. We will look a little bit in more detail. So I am plotting or drawing the differential version of the output driver. So and this, you can say, this is equivalent to the channel termination impedance, okay, which is 2 times RT. This I can say RP, Rn, and let's say WP by L and Wn by L. This one is your Dn and Dn bar, and the supply is VDD Tx. Now the simplified version of this output driver will be, wait a minute, that you have a resistance plus an ideal switch, so this is the same. What is happening? The same as VDD Tx. Now since I am making this as an ideal switch that has an impedance resistance of 0, so I will say this is equals to RT, 2 times RT, and node potentials are VOP and VON. And these switches are Dn, Dn bar, then this one is Dn bar and Dn. Okay, so in the actual output driver, what you see that the PMOS and NMOS are connected by the same control because they are complementary. So at a time only one will be on, and the output swing here will be VOP minus VON. Whenever it is on, it will be something as plus minus VDD Tx by 2. Is there any confusion in this? No, right? It is simple. And the current flow is, so the thing in the simple diagram is easier to understand, that PMOS and NMOS thing. So the current flow in, what is happening? The current flow in this is actually either in this direction or it is in this direction, and that is how you get a differential output swing of plus minus VDD transmitter by 2. Okay, now the question is that the impedance which I have drawn in the simplified diagram as RT, this RT should be equal to your RMOS plus RP. So let me call this as a RPMOS of a PMOS transistor and the poly resistance. Okay, and on the lower side that should be equal to RNMOS plus R poly resistance. It should be, it should actually satisfy that property to have a termination at the either side. Okay, now if your R poly is much greater than R MOS, then you will not see the variation, means the process variation due to MOSFETs are negligible. Right? Whereas your parasitic capacitance will be much more. So there is a penalty. Like if you make the MOSFET resistance negligible, then you can very well maintain a 50 ohm termination for these channels across the process variation. But the parasitic capacitance, there are two parasitic capacitance which will play a role. One is the internal node parasitic capacitance, and the other is the parasitic capacitance at the switching side. So these two parasitic capacitance will actually cause you a, so the internal node parasitic capacitance will cause you a data dependent output, which is like CP1 and CP2, whereas the input capacitance will cause more power consumption, let's say CP3, more power consumption in anything which is driving it. So there is a trade-off in in both the cases. Okay, so so the other design which we just saw very briefly last time, that the data dependency can be reduced if we use, let's say this as RP, and then you have RMOS at top and bottom. So this is your VOP terminal. So in this case, all the data transition always means if you have a CP parasitic, that CP parasitic appears on both the high and low path. Whereas previously it was different parasitic capacitance were appearing on different high to low to high and high to low transition. Okay. So in this case, now in all these cases, means you can design it for a typical corner or some particular process corner, but depending on your process variation and voltage variation, these capacitances will vary. Okay. So now if the capacitances will vary, not the capacitance, but the resistance of these MOSFETs will vary. So if you want to change them, what will you do? So let's say I design both the MOSFETs in typical corner. My R PMOS plus RP is equals to R NMOS, let's say call it this is RP1, R NMOS plus RP2 is equals to RT in my typical corner, 27 degrees Celsius, and let's say 1 volt supply. So this is what I will design. Now so if you have a process variation which actually sees quite a lot in poly resistance, maybe at plus minus 20%. So your RP can vary plus minus 20%. For example, your RMOS, depending on threshold voltage, that can, let's say, also varies plus minus 10%. So what will you do if you still want to have a channel termination? What are the options for you? And I still want to have the same output swing. So I do not want to compromise on the output swing. So you see, what are the parameters to here vary? The size of the MOSFET will actually decide what is the resistance of the MOSFET, right? And the other thing which will decide the resistance of the MOSFET is the control voltage. So you have only two options to deal with. Okay? So let's say to compensate process variation, to compensate PVT variation, you can either vary size or you can vary the control voltage. Okay. Now the thing is that your VDD transmitter is fixed because you want the same output swing, and to begin, if you want to use a smaller MOSFET size for PMOS, let's say you will use a 0 volt, you are not going below 0, and for NMOS you will use the supply, right? That is the beginning starting point. So what the other thing which remains for you? Means we have fixed VDD, let's say assume, and ground. We are not changing that part. Means I can very well say that I can go below 0 and increase or decrease below 0 to increase the MOSFET, to reduce the MOSFET resistance if we want, right? So if I want to vary the size, what should be the way? So let's say your RT resistance is equals to some n. So the way is where like to vary the resistances, you can use a number of segments and use only selected number of segments depending on the PVT variation. Okay, so RT is equals to, let's say, R MOS 0 I will call it because this is R MOS cell, plus your R poly 0 divided by n. That means at a time I can use n segments and get the desired termination resistance. And if this is in a typical corner, then for a SS corner, do you guys know SS, TT and FF process variation in system? Okay, so these SS, so the thing is in this thing CMOS process, you have different process corner which are SS, TT, FF, SF and FS. What it means is, let's say you pick up SF, right? What it means is that your PMOS is slow and your NMOS is fast. Okay? A PMOS slow means higher VT, and if NMOS fast means lower VT. So you can say in SS corner both PMOS and NMOS will be slow. In typical it is like a normal one. FF both will be fast, means both will have a lower VT. SF it is skewed on one side and FS is another skew. So the thing is, and this is a process variation which can vary by plus minus, depends on the process. So let's say you pick up a 65 nanometer process, your threshold voltage variation can be plus minus 50 to 100 millivolts on either side. So, and this is a statistical variation, means you do not know what is going to be once you fabricate it. So you have to compensate this process variation. So if, so just for example, I said that for typical, if you are using N cell to get a termination resistance, so what will happen in slow corner? So let me first ask the question in proper manner. In slow corner, both PMOS and NMOS threshold voltage will increase, right? If the threshold voltage increases and you are still operating with the same supply and ground, so what do you think the size will, you have to increase the size to get the same resistance or decrease the size? Increase the size. So that means that I need to have, let me just write it something else, let's say M, where M is greater than N, right? And it will be opposite case in a FF corner, where your threshold voltage reduces. At that time I need to reduce the number of cells to get the same RT impedance. So a conventional design actually uses so let me just write it as this as R MOS by N, RP, not by N, sorry, R MOS times N, RP times N, similarly RP times N, and R MOS times N. So if I use, I am just drawing a single end right now here. So okay, and I will use n such cells, nx, n times these cells. So I can choose a number of cells to compensate my process variation. Did you get that? So the way you can do is, means that's another simple circuit, that you can have a logic with a PMOS. So let's say there is a enable signal. And then you have actually a NOR gate, and this is your bit D, and this is enable bar. Let's see if it works or something. So I am using n times such cells. Okay. If my enable is high, then what will be then PMOS will be selected or not? So let's do this. No, if enable and D, let's say PMOS and NMOS, right? So enable, you can have all the cases 0, 1, 1, 0, 1, 1. Okay. So in 0, 0 case, your D is 0, enable is 0, you are basically getting 1. So PMOS is off. Sorry. Okay. And your NMOS is going to be, your D is 1, your enable bar is, because enable is 1, so enable bar is 0, so NMOS will be on. Whereas when you are having a 0 and 1, this is 0 and 1, 0, this is off, and your NMOS will also be off, right? Enable is 0, 1, 1, 1, 0, this is also off. So, and then when your enable goes 1, that time your 1 and 0, 0, this is off. So you need to work this logic, let's say. So this is enable, this is 0, 1, 0, 0, 0, this is on. Do you see this logic working or no? Okay, so let me just say, you can work out this logic, means you can, with an enable signal, you can select a cell or you can deselect a cell. You can use any complicated logic to do that. Now, when you use n number of cells, you can select and deselect. Now, what the problem do you think will happen if I use, let's say, 1000 cells? The output capacitance will basically increase, right? And what is the problem if I use only 10 cells? So, start with this way. Let's say you want a 50 ohm impedance. Your process variation is plus minus 10%. So you should have number of cells such that you can go from 45 to 50 and 55 to 50. You want both the ways, right? Now, when you want that, you can split that in 1000 cells. You can split that in 10,000. In 10 cells. It's still the process variation you take into account. What is the problem if you use n equals to 1000 and n equals to 10? Huh? So if you use larger, you get more resolution, but if you use lesser, you get lower resolution but lesser cap to begin. So that part will come actually when you are going to do an equalization with this. Okay, that we will look at later. So just here, let me say if n equals to 1000, you get higher resolution. Higher resolution to control means you can control even, yeah. Yeah, means I just assumed it, but you can change the, so it's like this. Let me just tell you. You can always choose a different size for PMOS and NMOS to have the same resistance, right? And why is it so that, okay, think it this way. You are using a poly resistance, which is some contribution. If you use a different poly resistance on both the sides PMOS and NMOS, then the thing is your MOS resistance will also differ. If your MOS resistance differs, then the process variation you will find it difficult to handle. Mean that requires then more number of cells. And the difference which we are having here is when we switch on and off any cell, we are switching the whole PMOS and NMOS. We are not doing it selectively like only NMOS or only PMOS. So you increase the size of the PMOS such that it has the same contribution to the total resistance as the NMOS contribution is going to be. Yeah, so the thing is, that is the corner, let's say SF. Like it is a skewed corner. So in a skewed corner, that is where your number of cells will come. So you will not be able to match a 50 ohm impedance on both the sides in this particular implementation. There is a way you can do it. So the other way to do is that so let's say my pre-driver for this is different. Okay. So means, let's say that looking in impedance, if you give the same supply, for example, this is equals to 49 ohms and this is only equal, this is 51 ohms. If it happens to be, if it's in a skewed corner, then what you can do, you can vary VDDH and VDDL to get RT equals to 50 ohm with same number of cells. Okay. So this part also is being done, that you use a different VDDH and VDDL for the pre-driver. The only thing is it adds more circuits in the path. Yeah. Bulk voltage? Bulk voltage control can be used, but it's not done that much. So the thing is, you tie the bulk to in most of these cases, you tie the bulk to either the higher supply for PMOS and for the NMOS. So bulk control means, yes, surely you can use the bulk control to change the threshold voltages and all, but that is not most of the time the exercise control. And the reason you can say that when you are controlling bulk of a PMOS, you are also basically adding the noise coming through the bulk. So this is if you do not do anything, think about it. If you do not do if you connect the substrate of NMOS to ground. So let me just pick up here. So the third terminal, right? Fourth terminal. So this is your bulk. And for PMOS, so ideally you tie it to VDD. And this one goes to ground. Okay. And when you lay it on a substrate, this ground is a substrate ground, which has quite a good contact to the substrate. But if you start giving this thing as some controlled supply, so that controlled supply ground can not be as good. So you have to then spend the effort. If you do not spend the effort on the controlled supply to make it like a perfect ground or a perfect VDD, you will start injecting noise here in both the cases. So this is surely a control but you should check for this, whether you are adding a noise or you need a proper control is coming right or not. Okay. Yeah, you can surely do that. So that particular, so I will tell the reason is this. If you try, so this is also, if you try to use a different number of P and N cells, now think of also the layout. So let's say I am using, pick some realistic number, let's say I am using for P cell, it's 64 cells, and what is happening? An N cell, for example, let's say 32, half of it. Okay. Then your P cell may be something here, and your N cell is P cell is this, then the N cell is something smaller in compared to size. And your signals are running all around. So, and then the other thing is, the load which is coming on the P will be higher. So anything which you are driving this, so you see this P driver, right? What is that thing? How are you going to place these P drivers? The input data to both of them are the same. So one other part is that when your PMOS is switching, your NMOS should also switch. There should not be any lag in between the two. If there is any lag, that will cause a change in the output, which is again data dependent. So ideally you want both of them to have the same transition. If you are laying out, because you are using a different number of cells, the layout will differ in the layout. So the control signals which you are taking into account, you need to then size these pre-drivers also in the same manner. And you need to check the exact transition point. You cannot just assume that I am giving D to the same pre-drivers. They are different loading at the, they are actually happening a different loading here, CMOS, CPMOS, and CNMOS. And I can just assume for like without putting any effort that it will work fine, it will not. So if the other thing is, if both the cells are at the same location, right, your PMOS and NMOS will be triggered by the same signal. There is no mismatch in the PMOS and the NMOS path. So that is what you need to take care of. Okay. Then so let's look at what is the maximum swing which you can see in the PMOS output driver can we go. So just look this example. So this is VDD TX, right? So the output swing, so this is called as a high swing because you are basically connecting to the supply VDD. It gives you like a VDD transmitter by 2, right? So if I say V out, okay, so here the question arises, what is the minimum swing can you get with this output driver? So it is not always needed that you always transmit a maximum swing which is available. Let's say it's a 1 volt process. You say I always will transmit a 1 volt swing. There is no reason if you are transmitting at a lower rate, you need to transmit a 1 volt swing. The loss is lesser, so you transmit lesser amplitude, right? Now the thing is, what is the minimum output swing can you think you can get with this output driver in an ideal manner? Okay, so pardon? Twice the amount of, no, I am asking the minimum. Yeah, so what will be the minimum voltage the CMOS can operate here? Huh? Maximum VT. So that is basically either your PMOS or NMOS gets cut off, right? So this is your V out minimum is equals to half of maximum of VTHP. Let's put it mod here if we are to, and V threshold voltage of N, right? So just have a look at it. A PMOS will get cut off when VGS of the PMOS is equals to VTH, right? So you have PMOS gets cut off when your VDD TX is equals to VTHP, right? And at that time the output swing means, forget what the sizes will be when it is operating very close to the threshold voltage. At that time the output swing will be VDD TX by 2. So that is equals to the VTHP by 2. Okay, that is if we only consider PMOS. Now you consider the NMOS, it's the same case. The NMOS at maximum volt means the supply which we are considering here, the NMOS will get cut off. NMOS gets cut off when your VDD TX is equals to VTHN, right? So it surely tells you that I cannot basically transmit a lower swing with this kind of output driver. And means take that bulk voltage you are right now not exercising, you can exercise that to change the threshold voltage. Maybe you can get a lower also. But that control we are not exercising right now. So what shall we do if we want a lower output swing? So is this point clear that using this P over N output driver you cannot transmit a lower voltage, lower supply swing, right? There is no confusion in that. Huh? V out minimum. So you are having, so this output driver, right? So if you look, VOP minus VON is your output swing, right? So what is this minimum output swing can it go? So you see here, right, that VOP minus VON is equals to VDD TX by 2. This part you get it right, right? So what do you think should be the, what should we should do to have a lower output swing? Huh? So, no, can you just go again? Mm-hmm. So are you saying this? What will that do? If this, first thing is if this resistance is connected, this is always on. Okay, you can do this. Yeah, but what do you think is the problem with this? So what he, no, common would be right. So what he is saying is, tell me if I am getting it right. What he is saying is, let's say if this R is, the R up is on, let's start using a terminology. This is on. Then he is saying if I want to have a lower output voltage, I can go and connect a resistance to ground. Is that right? So I can lower the swing here, and similarly I can do it here. Right? Means from the left side I am reducing the swing, from the right side I am pulling it up. So consider when only the current is flowing from, means if you see the current is flowing from R up on the left to R down on the right. In this case, if you want to have a lower swing, you can bring the left node down by using a resistive divider, and you can pull up the right node up, so you can get a lower swing. Do you get that? So, okay, just consider, let me go it in more. So what we are having right now is, when it is, let's say the output driver is operating in like this. So you are having R up, which is equal to RT. You are having R down, which is also equals to RT, and this is 2RT, right? So, and this is VDD TX. Okay. Now, so what is basically my, let's just say this is VOP, this is VON. So my VOP is equals to 3 by 4 times VDD TX, and VON is equals to 1 by 4 times VON TX, right? So if I want to reduce the output swing, what do you think? What he suggests is, I can reduce this output swing, VOP, by having a resistive divider here. Let's say something as Rx. This part makes sense, right? If you put a resistive divider between the same supply, you are surely going to have a lower. Means earlier, all the current was going in this direction. Now the current is, you are taking the current out. Yeah. No, yeah, we will come to that later. Let's say magically some magic happens and you have Rf plus Rx in parallel gives you RT. We'll go in maths in detail later. Okay, let's say you can do that. Similarly, I can actually pull this node up by using a resistance connected to this way. So what did I do? I reduced VOP and I increased VON. Yeah. Huh? Yeah. No, right? One is connected to VDD, other is connected to ground. Okay. So in this manner, what we get is, if I reduce VOP and increase VON, the overall result will be VOP and VON reduces. Okay. But what do you think is the drawback of this? Huh? No, DC I can always manage. So the thing is, I will switch this on only when DN bit is, so the top resist, so the thing is, first thing is, okay, the resistance which I have put here as Rx, that is not an always on resistance. The resistance is also a switched resistance. It comes into action only when I want it to be a lower voltage. What do you think is the problem with this? But how do you know the current here is more or less? So, okay, so let's see what the current will be, okay? So, let me just write it in a more right fashion. So, let's say this is R up, this is R down. So, I am using a symmetrical network on both the sides. R up, this is 2RT and VDD TX, right? And this network I can very well have, I am just writing an equivalent of that, VDD TX into R up by R up plus RD and R up parallel RD, and then you have a 2RT resistance, and then the similar thing will be, oh man, similar thing will be from the left hand side. So this will be VDD TX times R down by R down plus R up. This part is clear, right? Means I am just, so I am writing an equivalent of this as this, you can say. Huh? What? Uh-huh. No, this is the equivalent from this side. So I am just writing the equivalent from both the sides. Yeah, what's the question? No, we are not sending the same current. That will not. So you can say you are actually bifurcating the current through the output resistance and through the down resistance. That is what is actually happening. So first thing is the total current which is coming from the supply we do not know right now. Huh? No. So that will not happen. That's what I said. That I will always, means the resistance which you are seeing Rx, that is coming with a switch. It is not like it is always connected. So if I want a lower swing, I always have a switch connected to the resistance. Then I will. Earlier you were only like switching on the resistance connected from VDD to the output node. Now you can say you are having two resistances. the way I have drawn here is means you have an R up resistance connected with the source. So this is the branch now. So you switch on both or you deactivate it. So do you get the equivalent, simplified equivalent of the circuit from the left side and the right side? Right? So now your VOP minus VON, which is your output swing, what should that be? So you can simplify it in this manner. Let me just say that the center of 2RT will be equals to VDD TX by 2. That's the common mode voltage which will come up. Okay. So VOP minus VON will be equals to VCM. Sorry, let's not write this one. Let's write only VOP is equals to VDD TX by 2, which is your common mode voltage, plus RT divided by R up parallel R down times VDD TX into R up by R up plus R down. Right? Is there any confusion in this expression as such? I'm just writing a resistive divider. So you have the common mode voltage plus RT will be the VOP I am considering with respect to VCM, and the supply is VDD TX into R up by R up plus R down. Okay. So let me just simplify this. Oh man. VDD TX by 2 plus, if you see, this will be equals to 1 by R down times RT, right? So you will just need to expand this part. This is equals to R up, R down divided by R up plus R down. Okay, so things will cancel out, and what you have is then RT by R down times VDD TX. Okay, so by a similar expression, your VON is equals to RT by R up times VDD TX, just by symmetry, doing nothing else. So your VOP minus VON is equals to the expression, all right? Yeah. RT times VDD TX into 1 by R down minus R up. So just do a sanity check that when we were not having the down resistance, right, when we didn't have any down resistance connected to ground in this figure, right, that means R down tends to infinity. Okay, so if R down tends to infinity, this term goes to 0, you have, and then R up will be equal to RT. So you will have, there's something wrong there, wait. Huh? Just, Oh, this is not this actually. No. RT divided. Where did you say is wrong? R down by R down plus RF, right? That's what I have written here. No. So this is R down and this one is R up. Huh? Okay, so let me just see. You have R up by. Oh no, actually I think this is wrong. Sorry. From the left side, this is actually equals to VDDTX. It should be R down here, not R up. This was wrong, eh? R down by R up, so this is fine. Now you have first video dx by 2 and this should be equals to RT divided by R up parallel R down. So R up so let me just write it as actually there is one other term missing, wait. Okay, so let me get this. Wait a minute. No, this thing has gone bad. So let's just make it as a. So this one is right, no? VDD TX into R down by R up plus R down. Okay. And the equivalent is R up parallel R down. And then you have a resistance to common mode, which is actually common mode is VDD TX by 2. Right? And this node is VOP. So VOP is equals to RT by R up parallel R down into VDD TX times R down by R up plus R down plus R up parallel R down by RT plus R up. This term was missing earlier. Yeah. You can work that out. So, okay, let me just tell you. So, why the middle point? So, if you look at the middle point, right, VCM. So, let me just write the expression for VCM. VCM will be equals to RT plus R up parallel R down divided by 2 into RT plus R up parallel R down. From the left and the right side is the same thing, right? If you see this, from the left and the right is the same. Pardon? Yeah, voltage is on that. So I am coming to that. So this is just the resistive divider. Okay. Into R down by R down plus R up times VDD TX. So did you get this term? So in the end, what do you have? R down plus R up, right? So it will be, you will see this thing in this equal to use like VDD TX by 2 is used in many easier simplification. Okay. So where we were writing, I got messed up with this equation. So now, okay, coming back to VOP. Your VOP, okay. So what do we, so now let me just more simplify it. One thing where what we have is that R up parallel R down is equals to RT. This is the condition which we need to use for channel termination. Okay, so this will make, let me just bring it back here, your VOP is equals to, okay, this one what did I write here, RT by, oh man, can you just verify this equation VOP? I don't think. So this is your supply voltage, right? And the divider is RT by R up plus R down. I just made this a simplified cell. Okay. So now when I write this, oh man. Okay, so what you have is RT, R down, R up, R down by, or let's just write it as simply, because we are having R up parallel R down as RT, and this is R up plus R down times VDD TX. This is the left hand side of the equation, and this will be equals to plus RT by 2RT times VDD TX by 2. Means you see R up parallel R in both the cases, that R up parallel RT is equals to RT, right? R up parallel R down. So this is equals to R down by R up plus R down VDD TX plus VDD TX by 4. And your VON is equals to R up by R up plus R down VDD TX plus, is there anything missing? So where? Which one are you talking about? So we have this expression VOP. RT by RF parallel. Oh man, this one is, sorry, this one, right? So this thing gives you, here it will give you 2 RT. So you will get this 2 factor here, right? So 2 and 2. Okay. Now let me just write it in a manner which we can use better. So let's say I multiply R up and R down by R up, R down. Okay, so this will be 1 by R times up minus 1 by R down times VDD Tx by 2, right? Now we know that this is equals to R up parallel RD, which is equals to RT. So I have VDD Tx by 2 into RT, 1 by R down R up minus 1 by R down. Okay. So now let's do the sanity check that if I didn't have the bottom path which I wanted to use for a lower output swing, at that time R down tends to infinity and R up tends to RT, or equal to, it's not tends to, I can write just, because we still want to hold that case that it is matched. So this implies that VOP minus VON is equals to VDD Tx by 2. Right? Now look what is the, so if you basically, you can see here that if you play with R up and R down, you can create a different output swing. Okay? Now look at, what's the time now? Okay, so I think we will take the current consumption in this kind of output driver next time. Okay, so let's stop here.